Now let's take a look at this real-world example of a thunderstorm, what it looks like looking outside the airplane, looking at your cell phone or iPad on the internet, what it looks like at aviationweather.gov, and what it looks like on the onboard weather radar on the aircraft itself. So for starters, we can see, yes, there's a big thunderstorm over the airport off our left to the east as we're flying southbound here, and off our right to the west, it looks pretty clear. That's backed up with what we see here on aviationweather.gov as this airplane's approaching GSO, Greensboro, North Carolina, and it's also backed up with what we see here on our iPad on a weather app showing a storm approaching the airport from the southeast. Now, as the aircraft descends below the clouds, obviously it's going to get a little darker because now we're below the clouds. There's lots of moisture, lots of water in those clouds blocking out the sunlight, and it's approaching evening time as well. This is getting close to 8 p.m. Eastern time. As the aircraft is on approach, we can see some lightning flashes off the right as they're approaching to land on runway 5 left. And we can see those radar returns from the onboard weather radar on the aircraft showing the storm still off their right. Good reason they're landing on runway 5 left. Now there's something very important to note here about the onboard weather radar. Notice the tilt is at plus 4.2 degrees. Very similar to how the tilt works on the radar ground stations, where they take several scans of the sky at different tilt angles and then compile those images into a radar mosaic, into a composite image. We know that takes about 4 to 11 minutes to occur, and that's not good when you're in an aircraft that's moving 6, 8, 10 miles in a minute in these really high-speed jets. That is why the tilt is specified right at 4.2 degrees and is not moving up or down. It's simply scanning that one slice of sky just to grab the image and give you the immediate information there. So it's up to the pilot to control the tilt here. It's not making a composite image of several tilts as a ground station would. It's simply looking at one slice of sky. Of course, if the pilot tilts it too far down, you may wind up with some ground clutter, as you do here. And then when you see very large returns, like we do here on the right, obviously that's going to have to be some sort of mountain, some sort of large terrain, or in this case, it is in fact a very large thunderstorm with lots of water in it. Now, as soon as this aircraft landed, there's so much lightning in the area that they were stuck out waiting for people to come from the FBO to guide them in. So we get to watch out the window as the storm moves over, as well as looking what the onboard weather radar is showing us here while they're on the ground. It still works while they're on the ground. They obviously just have to tilt it up high enough that they're not getting too much ground clutter or too much interference from anything that's above the nose of the aircraft where the radar is located. We can compare what we see on the onboard weather radar to what we see on the iPad, just using the internet as a connection to see the radar images that are being gathered by ground stations and then compiled into that radar mosaic that's then sent to us via the internet on our iPads or cell phones. And we can also compare the METAR at the time the aircraft landed to the updated METAR just about 15 minutes later when another aircraft had come in on final and reported a 20-knot gain of airspeed on final. So a large increase in performance. That's a huge warning sign that you may get that decrease in performance, and gaining 20 knots is not good, but losing 20 knots, of course, is even worse. That aircraft was able to land safely, but look at how the METAR changes between these two times. So we have the time that the first aircraft landed, and then just 15 minutes later, as the storm is getting closer and closer to the field, we get the gust front that comes out of that thunderstorm. As all that water is falling down, all of that cold air is falling down, it hits the ground in a one large giant downdraft, and then has to go somewhere, and it turns into horizontal wind that causes very severe wind shear on takeoff and landing, as well as just very strong surface wind around the airport in general. A good takeaway from this video is, although the radar imagery on the aircraft itself is just at a single tilt angle, it's instantaneous almost. It only takes a few seconds for that radar to scan and then display that information to the pilot of that one slice of sky, compared to the ground stations taking perhaps a more accurate or more complete image of the sky with several scans at different angles. However, it takes much longer, 4 to 11 minutes, for those ground stations to compile all that data and then make an image, and then for it to actually go out to separate weather providers that'll make it through to your cell phone or your iPad through an app such as this, and then come to you. So you could be looking at data that's easily 15 or 20 minutes old when trying to make decisions on whether or not you should land at an airport, compared to the advanced onboard weather radar that corporate jets and airliners have on board that help them to avoid these storms. Keep in mind that your ADS-B weather, if you're getting ADS-B weather into your cockpit, although it's wonderful, it is still subject to those same delays that all devices experience. So your iPad, your cell phone, all that ADS-B weather is coming from ground stations, and it takes time for them to scan the sky, make that radar mosaic image, and then pipe that through to your aircraft via ADS-B or whatever other means. The only truly accurate image of what is happening right this second is going to be onboard weather radar from a radar dome on the actual aircraft itself.